Hi guys, this video is our practice test for Unit 5 Exponential and Logarithmic Functions. Show all work for full credit. And in problem 1, the value of a truck Y in dollars can be approximated by the model Y equals 54,000 times 0.8 to the T, where T is the number of years since the truck was new. We have to tell whether it is growth or decay. So here I have some notes from class, which we have up on our as a poster. And growth happens when our base is greater than 1. So we have a 1 plus a growth rate, R. R is our growth rate. And decay happens when the base is less than 1, so we see 1 minus R, decay rate. You might not actually see the 1 plus R, 1 minus R. Instead, you're going to look at the base and just judge, is that bigger than 1 or less than 1? And 0.8 is less than 1. So all you need to say is that this is decay. But then identify the annual percent increase or decrease in the value of the truck. Well, we could rewrite this as 1 minus 0.2. Therefore, the truck is going down in value by 20% each year. So the percent decrease is 20%. What was the original value of the truck? All you need to do is look at the number in front. It's called the A value right here, so 54,000. And that makes sense because if we plugged in T equals 0, anything to the 0 power is 1. So we have 54,000 times 1 right at the beginning. So 54,000 is the original value. Estimate when the value of the truck will be $30,000. You may use a calculator and you don't have to solve. So what they're talking about is get your calculator and actually plug in that function into Y equals. So I have 54,000 times 0.8 to the X power. You can graph it, of course, to see, but since it's starting at 54,000, we're probably not going to see this very well in the graph right now. More useful is to look in the table, and we are looking for where is the value $30,000. So that would be the Y value at 30,000. So here I can see it's around 2.6 to 2.7, right around there. So either answer would probably be fine. I think I'll go ahead and select 2.7 years. Later on in the test, we'll have to solve, but here it just says look on the graph, look on the calculator. All right, let's take a look at problem number 2. Your parents invest $1,000 to save for your college. Option 1 pays 5% annual interest, compounded quarterly. What would be the amount after 3 years? We have an equation to use for compound interest. There's 2 of them. One is when the interest is compounded at regular intervals, and one happens when the interest is compounded continuously, and we are comparing those two. So we're using the first equation for part A of this problem. So I'll write that equation down right here. It's the amount equals the principal times 1 plus R is our rate in decimal form, N is the number of times per year, and then N appears again and in the exponent times the time in years. So 5%, let's see, we're looking for the amount and we're starting with 1,000, that's called the principal. The 5% is the rate, but we need to write that as 0.05. It gets divided by however many times per year we're getting the interest, and that is quarterly, so 4 times per year. To the 4 times 3 power, because it said what would be the amount after 3 years. We really just need to compute this in the calculator, and usually I just jump to knowing what the exponent would be. In this case it's 12. Otherwise you can just enter it in the calculator using parentheses. So here I have 1,000 times 1 plus You don't even need parentheses here because of order of operations. It will divide 0.05 divided by 4 before it adds it to 1. And then to the 12th power, that part I've already computed. So it looks like we have 1160/75. In part B, we're using the continuous compound interest formula. A equals principal times e to the RT. So here we have 1,000 times e, and the rate is 4.5, 0.045, and the time is the same, 3 years. Let's put that into the calculator as well. So 1,000 times second ln will give you e to the 0.045 times 3, and this one is 1144.54 if we round up there, so 1144.54. So we can compare, although it doesn't ask you to, but we can compare that you're getting a little bit more money by having a higher percent interest compounded quarterly rather than a lower interest compounded continuously in this particular scenario. Part 3, the amount Y in grams of the radioactive isotope phosphorus-32 remaining after T days is Y equals A times 0.5 to the T over 14, where A is the initial amount in grams. What percent of the phosphorus-32 decays each day, and show your work. This looks very complicated, but really we're just taking the equation we have and we need to convert it into 1 minus R, that decay. So we're looking to just use some exponent properties here. So original equation, y equals, it doesn't matter what the A is. We're going to use power property to pull apart the exponents into 0.5 to the 1 over 14th power to the t. So it's getting closer to the 1 minus r to the t. We only want a t up here. Now we can actually just compute what is 0.5 to the 1 over 14 power. Just remember to put parentheses around 1 over 14. It's the 14th root, and it's 0.951695, so 0.95 would be fine if you write that down. That's totally fine. And then again, we want it to look like 1 minus r. What is 0.95? Well, it's really 1 minus 0.05. Now we know our rate is 0.05, or about 5%, because the question asks what percent decays each day. So 5% decays each day. Problem 4, we're using Newton's law of cooling and showing all steps. It says you're driving on a hot day when your car overheats and stops running. The car overheats to 300 degrees Fahrenheit and can be driven again at 225 degrees Fahrenheit. It is currently 85 degrees Fahrenheit outside, and the cooling rate of the car is 0.00075. How long do you have to wait until you can continue driving? You need to know how to plug things into the equation. The T over here is the temperature you want the car to be. It says it can be driven again at 225. T sub 0 is the original temperature of the car, and it overheated to 300. T sub R is room temperature, or in this case, outside temperature, and that is 85. Times e to the negative, because this is decay, and the rate was 0.00075 times your t. Again, plus your room temperature, or your beginning, or your outside temperature, which is 85. Here we need to show all steps to solve for t. What we're trying to do is isolate the e to this power involving t. So we're going to undo all the steps with reverse PEMDAS. So undo your addition and subtraction first. Subtract 85 each side. $225 minus 85 is 140. At the same time, I'll do what's in parentheses here. 300 minus 85 is 215. Now to undo the 215, it's being multiplied, so we're going to divide each side by 215. 140 divided by 215 is 65.1, or sorry, 0.651, and that equals e to the negative 0.00075 t. We have the e isolated, so at this time we want to rewrite it to be able to get t out of the exponents. We're going to think about a log. Log base e is otherwise called ln, or natural log. So here we have log base e. The answer, or the argument of this log, is going to be 0.651. And logs give us the exponent, so the exponent is negative 0.00075 t. Last step to get t by itself is to divide by that crazy number. Now let's use the calculator and figure out what that is. So we've got natural log of 0.651. Close that parenthesis and divide by negative 0.00075. So this is a pretty big number. It's 572.3 minutes. Let's divide by 60 to get that into hours. It's saying we need to wait 9.5 hours. I'm going to check that answer later, but right now I got 9.5 hours. Seems like that's a long time, but I guess it makes sense considering it's so hot out. On the back side, we have the average number of free throws a basketball player can consecutively make during practice is modeled by the function f of x equals 1 plus 1.3 times the natural log of x plus 1, where x is the number of consecutive days the player has practiced for 1 hour. After how many days of practice can the basketball player make an average of 5 consecutive free throws? Solve and show all your steps and round it to the nearest whole number of days. So this function is modeling the number of free throws, and we want to know how many days of practice, after how many days of practice can they make 5 consecutive free throws. So the y value, or the function value, is where we're putting that 5 into. Similar to our last problem, we want to isolate the natural log in this case. So we're going to undo everything else that we can. We can subtract 1 each side first. 4 equals 1.3 natural log of x plus 1. We can divide each side by 1.3. .0769. I just keep a bunch of decimals until the very end. And now we can't divide anything. We just have natural log. So it's time to rewrite. This is base e. So we're going to say our base is e. What is our exponent? Well, logs tell us the exponent, so our exponent is this decimal, 3.0769. And the answer is right here, x plus 1. We're going to evaluate e to that power. So I use second answer to use my last calculation as my exponent, and I got 21.69. Subtract 1 each side, and you're going to get x equals 20.69, but we need to round that. Like I said, round to the nearest whole number of days. So you're going to round up, so it's going to approximately equal 21 days. 21 days of practice. And we're on our last problem, which is just to solve and show steps. So in problem A, we want to find or create the same base on each side, because you can see we have 27, that is a power of 3. So we can just rewrite 27 as 3 to the third. Once we have the same base, you can equate the exponents, property of equality. 2x minus 3 equals the exponent 3. And that's easy to solve from there. Add 3 each side, and I'll just skip showing every step, but that's okay on this part, even though I say show all steps. So 2x equals 6, divide by 2, and x equals 3. Over here we already have natural logs, same base on each side. They're both base e. We can equate the answers to the logs. So 2x plus 3 equals 5x minus 6. Subtract 2x, and then you're going to get a 3x over here. Add a 6 each side, and you're going to get a 9. Divide by 3, and we have x equals 3. Part C, we have 1 log, so let's rewrite it. Base 3. The base is 3, the exponent is 2, and the answer is 4x minus 7. 3 squared is 9. Add 7, we have 16 equals 4x. Divide by 4, and x is 4. In our last problem, we do not have 1 log. We have 2 logs. So we're going to use the product property in order to condense the 2 logs into 1. So they're both base 4. We're going to put them together now, and we have negative x, and we have x plus 10. Both go into the answer of the log product property. Let's distribute right here. So negative x times x, and then negative x times 10. Negative x times x is going to give us negative x squared. Negative x times 10 is minus 10x. This time we have 1 log, so let's rewrite this as exponential. The base is 4. The exponent is 2, because logs tell us the exponent. The answer is negative x squared minus 10x. So we have 16 equals negative x squared plus 10x. I'm going to take this all over to the left side to make this coefficient positive, because this is quadratic right now. So everything on the left, I would be adding x squared over here, adding the 10x, and then the 16 was already on this side. Factor this. What are some factors of 16 that will give you 10? 8 and 2. And these are both positive. In this case, you give positive 10 if we were to FOIL or box that to check. Zero product property means set each factor equal to 0, or just know P and Q are the answers to the quadratics, and the answer here would be negative 8 and negative 2. We have to check that those would work because we can't take a log of a negative number. So if we plugged in negative 8, we're going to have log of negative 8. So that's positive, so that's okay. And if we plugged in negative 8 over here, we're going to have log of 2, positive 2. So it looks so far like this could work. If we plug in our other answer, negative 2, we have log of negative 2, so that's positive 2. So that would work. And over here, we would have log of negative 2 plus 10, so that would be log of positive 8. In fact, both of these solutions work.